Hello Nimishka, a very good afternoon to all of you. 28 of you have been here. Now let's start with today's class. I can understand that Saturday afternoon is a very dull moment to have a lecture. Nevertheless, let's have it. Now, so far in this course, we have already talked about the basic idea of sound perception. We have spoken of how human ear responds to sound, and we have also talked about, or we have also learnt how to measure the sound intensity and what are the basic calculations involved. We will take it further today. Now, today I'm going to start with chapter 7, and that is a chapter that talks about pitch. Now, pitch is a very important concept both in day to day life and music as well. So, we are going to talk about it. We will look into the basic pitch scales. There are pitch scales are very elaborate, but we are going to look at some of the basics of the pitch scales, basically in the Western music and Indian classical music. And we are going to learn or talk about the pitch discrimination, how the pitch discrimination inside human ear and mind takes place. I hope you can all hear me clearly. So no problem solving in this lecture. So you can just relax, sit back and listen to me. Thank you. So going ahead, I will start with a simple experimental demonstration. And before we start talking about the pitch, remember we are talking about sound, and a lot of it can be done only by experimentation. Me just talking plain on the screen and you listening it will not make much of the sense. So let's go ahead with some demonstrations. Thank you, Alvin. Thank you, Simran. So let's have our first demonstration, our first little video for the day.
Hi, I'm Jared. Welcome to Fun Science Demos. And the big idea today is sound and how sound changes. Through science, we've discovered that the faster something vibrates, the higher the sound or pitch. And the slower something vibrates, the lower the sound or pitch. I can show you with my voice. La. My vocal cords are vibrating slower. La. They're speeding up. La. Speeding up. La. They're moving really quickly, so the pitch goes up. I can't show you that through my throat, but I can with these neat little demonstrations. I have rulers fastened to the tabletop. I have a guitar. I have a xylophone. And I'm going to fill a bottle of water to show you that science at work. So let's use these rulers. Again, the slower something vibrates, the lower the sound or the pitch. I can even see that ruler moving slowly. Well, the faster something vibrates, the higher the sound or pitch. Low, high. Slower, faster. Let's check out the guitar. Let's see if we can make that pitch higher by making it vibrate faster. The pitch goes up, the faster it vibrates. Now, let's try the xylophone. You can hear the sound and the pitch go up because that's vibrating much more quickly. This is vibrating slower. Slower, vibrating faster. Now, the water. What's making the sound in there? Well, I'm blowing across the bottle, and the air inside the bottle is vibrating. Slowly. Let's make it vibrate more quickly. I'm going to fill it up with some water. I have some blue food coloring just so you can see it. Now let's try. Oh, you can hear the pitch go up. The sound goes up because that air is vibrating faster. Let's fill it up even higher. See what it sounds like. That air inside is vibrating really quickly, so the pitch is higher. Science is so cool. Don't forget to check out some of our links in our video description. Thanks for watching.
So yeah, you could see that some of these observations are obvious and some might have been new. Xylophone, I hope many of you have tried. Scales, different lengths. So the general rule of thumb here is, as you must have noticed, a larger object, a massive object, one which has more mass, vibrates slower. A larger air mass in the bottle vibrates at a lower frequency or lower pitch. Higher pitch, which sounds shriller, generally are small mass and smaller in size. So that's the basic idea of pitch. It's a characteristics of sound that make it sound high or low that determines its position of a scale. For example, a male voice is typically a lower pitch voice, a female voice is typically a higher pitched voice. If you have a roaring of a lion, then it's a lower pitch voice but very loud. The humming of a mosquito or a honeybee is a very high pitch voice but it's a very low loudness. So that is how you can differentiate between loudness and pitch. Although there is a lot more ascribed to pitch, pitch is a very subjective sensation as well. So you are subjected to something called as, if you are, if you are not trained to distinguish between the two closely placed pitches, then it will be very difficult for you to figure out the difference. That we will talk later in this lecture. But let's go ahead. Historically, the pitch scale, Pythagoras has been assumed to be created the first pitch scale when he found that if you have a string and if you pluck it at different ratios, put a finger here, pluck at different ratios, you would realize that the frequencies are different, and in some ratios the frequencies are very pleasant and in some ratios they are not so pleasant. So they are called consonant and dissonant ratios. We are going to talk about them in the next class. So credit goes to Pythagoras so far to connect this music world to the mathematical world and for the discovery of octave, which is a basic unit in a pitch scale. An octave here means double. Why do we call it octave? We will discover it in a while. Let's learn some few things about Pythagoras.
The 6th century BC. Pythagoras, the famous Greek mathematician and philosopher, travels throughout Egypt over the course of 10 years to study the esoteric arts under various local priesthoods.
Pythagoras is certainly one of the most interesting characters that we see in Greek history. In 535 BC, Pythagoras left his home in Samos, Greece, and traveled to Egypt, where he was initiated by the Egyptian priesthood in all of the different secret societies and organizations that they had available. And from this secret knowledge, Pythagoras obtained information that seems very, very far ahead of his time.
Pythagoras one day was walking past a blacksmith shop and heard the sound on the anvils and got fascinated with sound and thought it could be understood mathematically.
Pythagoras, in hearing these tones made by the metal striking the metal, intuited that there was a mathematical relationship between the different notes in a scale. There was a proportional relationship of ratios between these different notes in the scale.
When you look at Western music, it all has its root with Pythagoras. And the great discovery he made is that the waves generated, say, by strings or wind instruments, could be converted into clear notes and scales by using fractions and discrete ratios. So we end up with thirds, fifths, fourths, octaves, by simply taking the string and holding it in these fractional ratios. You get sound in these ratios, and it's very pleasing and works very well to the human ear. So Pythagoras did this amazing job of taking math and geometry and tying it to music, which then led to the entire Western musical scale.
Pythagoras' revelations regarding sound and music led him to speculate that the universe itself and everything in it is in a constant state of vibration. He theorized that there is a harmony throughout the cosmos, and that even the planets emit their own unique sounds.
Pythagoras thought of the universe as operating as a harmonious whole, which he compared to a lyre, an instrument that is a little bit like the modern harp in that it has different strings. Each string vibrates at a different frequency, producing a different sound. He thought that each planet in the solar system vibrated at its own unique frequency and produced what he called the music of the spheres.
When you look at the individual planets in our solar system and around the universe, radiation that's emitted in each planet will be in its own frequency range. We can convert that to an audible signal and think of each planet having its own signal or tone or music that goes with it.
So that's an important discovery there, that if you have strings and if they are of different lengths, then they will give you different sound. These lengths can be put geometrically and algebraically in ratios, which are called Pythagorean ratios. We will come to that in the next chapter. Some ratios are consonant, that is, they sound pleasant. Octave is one of them, and some ratios they don't sound pleasant. We will look that also. Now, to answer this Jay's question, what is the difference between pitch and the frequency? If anyone can comment, it's fine. We will look greater into it, but right now, as we had discussed in last few classes, the difference between a stimuli and pitch, stimuli and response. So frequency is a stimuli. So a source produces frequency, pure frequency or whatever. But the pitch is the sensation. So if a source produces a particular frequency, human ear can may or may not sense in the same way. And that's why the word pitch comes to it. So what we make sense out of frequency is basically pitch. So, for example, a musical instrument may play the same note, but two different listeners can ascribe it at two different positions on a musical scale. So, they may say that it has two different pitches depending upon many factors, and we will come to those factors towards the end in this class. So, right now we are talking about octave, which was, we assume, that discovered by Pythagoras. An octave is a basic unit. The other units of music are either multiples of octave or subdivision of octave. The octave stands for 8 or octa. Octa means 8, 8 steps. So at the frequency ratio between the highest frequency and the lowest frequency in an octave is 2 is to 1. Now remember, the octave is basically used in word is used for Western music. In Indian music, there are seven steps or saptam or septa, something like that. Here, the eighth step is the beginning of the next scale. Why are they important? Because if the ratios are 2 is to 1, which is observed by Pythagoras, then the strings sound in a very similar manner. So similar sound or consonant sound. That means if two important thing about octave is that if two musical notes are an octave apart from each other on a scale. Octave apart means if octave means double, remember when an actual number comes. So if it is, why do we call it octave? I'm going to get into one more video to explain it. But if the frequency is double than the first one, then it sounds similar, and that is what is called consonance or consonant sound. Octave in Western music is further divided into 12 intervals, which is called semitones. Remember that I've always told earlier also that human ear is a remarkable device. Human eye can only sense up to one octave. If you take red color as your base wavelength and violet as or blue violet as the highest wavelength, smallest wavelength or highest frequency, red as lowest frequency, then the ratio is approximately 2 is to 1. So human eye can see just one octave of electromagnetic spectrum, but human ear can sense up to 10 octave from 20 hertz to 20,000 hertz. So can sense up to 10 octaves of sound. Although, as I said, the ability to hear sounds at a higher octave diminishes rapidly. So most of the musical scale don't go beyond 3 octaves. So we will going to look that as well. So I have a small video which will demonstrate various
If there are only
concepts to
12
us.
swaras, why is it that the harmonium, the keyboard, and the piano have more than 12 keys on them? Are you wondering why? Do you want to know the answer? Well, then I think I have the answer to your questions. Welcome to the third episode of the Basics of Indian Classical Music with me, Anuja Kamath. In the previous episode, we learnt about the concept of swara. In this episode, I shall introduce you all to the concept of saptak, which is a melodic concept related to the concept of swara. So yes, let us begin by understanding the theoretical aspect of the concept of saptak. The tonic note sa is the root of Indian music, and as discussed earlier, the position of the other notes depends on the position of sa. When the frequency of this sa is made double, we get the upper sa or tar sa. The frequency space between these two is called the saptak. In terms of swaras, the saptak is represented by 12 notes as we have understood in the previous episode. But the name saptak is derived essentially from the word sapt, meaning 7, indicating 7 main swaras. The upper sa is theoretically not part of the saptak, and it is said to be the start of the next saptak. However, practically it is essential because it gives a closure to the previous saptak. In Western music, saptak is called an octave, octa meaning 8, because the 8th note or upper sa is also considered a part of the frequency space. In Indian classical music, generally 3 octaves are brought to use. First is the middle octave or madhya saptak, which is the original octave. Then is the lower octave or mandra saptak. The frequency of the swaras of the mandra saptak is half of the frequency of the swaras of the madhya saptak. The swaras of the mandra saptak are represented by a dot below them. The third octave is the tar saptak or higher octave. The frequency of the swaras is doubled that of the swaras of madhya saptak. The swaras of the tar saptak are represented by a dot above the swaras. This is the audio example of the 3 octaves. Mandra saptak. Madhya Saptak. Tar Saptak. The keys on a keyboard can easily make the concept of octave visual. Any set of 12 consecutive black and white keys represent a saptak. So if you take black 2 as sa, then the next black 2 will be the upper sa, which will be of double frequency of the original black 2. Thus it marks the end of that octave and the beginning of the upper octave. Similarly, you go 12 keys down from a key, you will get a lower octave. Generally for females, their scale or pitch is Kali Char or Kali Pach, that is, their middle octave starts from black 4 or black 5. For men, it is generally Kali Ek or Kali Do, meaning their middle octave starts from black 1 or black 2. So in Indian classical music, each person can thus choose their pitch according to their comfort level. In case of vocal music, the concept of the three saptaks can be roughly compared to the concept of the three vocal registers of Western music. Basically, one person's Madhya Saptak might not be the Madhya Saptak for the others. Because, as discussed earlier, the individuals choose their Madhya Saptak depending on their comfort levels. Madhya Saptak is the frequency range in which a person can sing with ease. It can be compared to the middle register or voice, that is the voice which is full-throated and the vibrations of the voice produced resonates at the throat. While the Mandra Saptak can be compared to the chest register or voice, which indicates that while singing the notes of this Saptak, the resonance of the voice produced is felt at the chest. The Tar Saptak can be compared to the head register or voice because while singing the notes of this Saptak, the vibrations of the voice are resonated in the cheek area of the head. So now it's time for the practical application of the concept of Saptak to a lighter music form that you are acquainted to. I think the concept of Saptak comes up very well in this song from Devanandji's movie. The song is called Hare Rama Hare Krishna. In this song, Usha Uttab ji sings the lower octave part while Asha Bhosle ji sings the...
Okay, that's fine. So, yeah, that clearly explains the existence of an octave scale originally uh, obtained by Pythagoras and later extended to various music traditions all over the world, be it Western, be it Indian. You can explore that video further on YouTube. Uh, the if you want to look at the example of the song. Now I'm going to take the last topic of today's lecture, and that is pitch discrimination. And as I said, uh, the frequency produced by an instrument is one part of the experience, but how the human mind and human brain responds to it, that becomes the other part of the, and that part is actually related to the pitch. So we generally calculate pitch by changing the stimuli slowly so that the human brain can begin to differentiate between the original and the next ones. There will be a slight differentiation. So ability to distinguish between two nearly equal stimuli, it is called just noticeable difference, delta F. And you can see that the just noticeable difference varies as critical bands varies. So, and it is not surprising because when the two notes here, as I said, critical bands are on the same critical band, you won't be able to distinguish between them. As you go on the another critical band, you will be able to distinguish. So two notes, say playing around 100 uh, hertz, if they have to play fairly close to, I mean, you can resolve to fairly closely playing frequencies at a lower frequency. But if there are two frequencies playing at a higher frequency, and if you have to resolve them, they has to be played with a larger difference because the critical bandwidth increases and even delta F increases. So that is what the meaning is. It also depends on frequency, the pitch sensation. So if your playing pitch is higher, the pitch sensation ability to distinguish between the two pitches is going to be higher, etc. It depends on the sound level. Sometimes a higher pitch playing at a lower sound level may appear to be of a lower pitch compared to a simultaneous lower pitch playing at a higher sound level. So sound level plays an important. The duration of tone also plays an important role. One frequency played for a longer duration, other frequency played for the shorter duration, then distinguishing pitch can be challenging. The longer duration tone will dominate in pitch compared on the other one. So that is a very important parameter also for your pitch registration. In fact, the last class or last to last class, I had put some demonstrations on masking and I had left a link in the description. So please go through that link. That link also has these kind of demonstrations on pitch, and also depends on suddenness of frequency changes. So if the frequency changes very fast, the pitch will appear to be different. If the frequency changes slowly, then pitch appears to be different. So that is another aspect of it. Then the training of the listener, another important thing, that the if your ears are not trained for the kind of music, then or kind of pitch discrimination, then that will also play a role. I myself, I am a physicist and not trained much for the music, so I need to take help of some videos and other things to put the concept forwards, so that it helps. So training of the listener is very important. Few of us must be trained for listening to classical music, and they can distinguish between various tones and pitches more effectively. So yeah, I mean, as I said, this is a first lecture in this subject. We will get into deeper into this chapter later on in the next class onward. So we end this lecture here. Thank you.